Hello everyone, my name is Justus Henneberg. I'm from Johannes Gutenberg University in Mainz in Germany. And this is my research project Northlight, together with Felix Schuhknecht, Philipp Reutter, Nils Brast and Peter Spichtinger. Let's jump right into it. So this is a climate researcher, and this climate researcher has an analysis task he's trying to solve. The task is to find, for this example, the highest temperature value in the marked region. And we can see the marked region on the right-hand side of the slide. Now this task might sound trivial, but this is frequently done for data quality assessment and also to compare two data sets with each other. So it's actually quite common. And there are a lot of existing array engines specifically for this task. So for example, there's FastTensor or GeoRaster or Rasterman. And so there's a lot of options to choose from. However, what we've observed is that in practice, these systems aren't used at all because they're complicated to use and complicated to set up and complicated to learn. And so what climate researchers usually do is write their own Python or Julia scripts from scratch, and that will do the trick. However, especially when the dataset gets larger, these scripts will stop scaling and they will become very slow and very memory hungry and so on. So this is not an ideal solution. However, we can also express this problem using conventional SQL. And that's quite easy to read and easy to write. However, it's not that easy to run on the data sets that are used in atmospheric physics. And this is a problem that Northlight tries to solve. So Northlight connects the atmospheric physics data sets and the possible optimizations that are due to these new formats to Spark and SparkSQL to allow for distributed execution of data analysis queries. Now, to understand why this is relevant, let's just look at the data format used. The data format is called netcdf, and that's the de facto standard in the climate research environment. This example here shows a slice from one of these netcdf datasets. So this is the temperature at a certain altitude, and you can see one dimension corresponds to the latitude and one dimension corresponds to the longitude. Now this is a single observation, but in a dataset there are usually multiple observations, and in netcdf it's common that these are materialized as separate files. So one file for each point in time, and this ERA 5 dataset has a resolution of 1 hour. So every hour there's one file that contains not only the temperature but also other variables. And I've said that this is a certain altitude level, and of course there are multiple altitude levels stored in the file, and so the entire dataset looks more like this. And you can see this is quite difficult to navigate already. So the important thing is, given this large amount of data, can we only load the data part that is relevant for our query? Because, as you might probably have guessed, the analysis queries usually scale linearly with the amount of data loaded. So this is an example here. We can see the more latitudes we load, the slower the query gets. And so if we're not interested in all latitudes, we better load every latitude. And this is where Northlight comes in, because Northlight just plugs into any existing Spark installation. So as you can see on the right, this is a Spark installation. There's the high-level SQL and data frame interface, which eventually compiles down to the RDD operations that produce the result in the end. Now Northlight introduces a custom type of RDD, and that's nothing new by itself. But Northlight also introduces schema inference and more common metadata inference, and uses this to optimize any query that targets a netcdf dataset. We'll see how that works in just a moment. So back to our query. Let's use that as an example. this is the region we want to load, and we only want to load this region. Now, if we were to do this manually, we couldn't write it like this. We'd have to write it like this. This is a Scala example, but it would work the same way in Python or Julia. So netcdf internally is stored as a multidimensional array. And so we first have to find the offset of the data we're interested in within the file, and then the extent in array elements along each dimension. So you can't say, I want my latitude to be between -60 and 75, but you have to say, read everything from 60 to 601, which is a lot less intuitive. But if you do that, you will get the data you requested and only that, and you will get it as a dense array, which you have to interpret for yourself. Now, what Northlight does is Northlight does this conversion for you. And so this query is transformed into the same load operation. So only the required data is loaded. And Northlight will also transform that data into a row-wise representation, which in my opinion is a lot easier to work with for most queries. Now this is a rather simple example. Let's look at a more complex example. Oh, well, yeah, here, of course, you can see the difference in data loading performance. Yeah, so the salmon colored bars is basically load the entire file, and the blue bars is using Northlight to prune unneeded columns and also to prune unneeded regions of the data set. And so you can see that, again, this scales linearly with the number of loaded columns and the number of loaded latitudes. Back to a more complex example. Now the user requests a larger region of the dataset, which actually consists of two subregions that overlap each other. And what you can see here is this query is in a form called disjunctive normal form, or DNF, which means that basically the query consists of regions that are connected by ands, and these regions are connected by ors. So these regions overlap. The question is, can you just use two read operations like before to get this part of the dataset? And the answer is unfortunately not. It would work in this case, but that's kind of not the standard way. And that is because this overlapping region is loaded twice. So if you're doing an average, that would bias your results. And if you're doing a histogram, that would also invalidate your results. Now, how do we deal with this? We need to split one of the rectangles at least into multiple smaller rectangles so that no rectangles overlap each other. And you can see the original rectangles in the top left corner. And you can see a few decomposition variants in the remaining corners. So there's like a very trivial decomposition on the bottom left, and there are more sophisticated decompositions on the right. Northlight would choose the decomposition on the bottom right because that matches the storage layout of the netcdf file, and so you gain an additional bit of performance from choosing this decomposition. Again, this decomposition is done automatically by Northlight. The user doesn't have to do this manually. Well, that's all cool and good, but let's look at an even more complicated example, which is this one right here. In this example, the user requests a large region which has some part cut out. And you can see this in the query, there's a knot, and the knot defines the region that is cut out. So how do we deal with this? Well, I mean, you could load the larger region and just manually filter out the smaller region afterwards, but that would still require the data in the filtered region to be loaded, which is something we don't want. And so what we've seen before is that queries in disjunctive normal form are very easy to translate into rectangles. And so this is what we're doing right now. We're just going to transform this query into disjunctive normal form, or rather Northlight does it automatically. And first eliminate the knot. Now rearrange the term. Now we arrive at these redundant filter predicates. So we just use the more selective one, and we're left with this arrangement of rectangles. Now again, these regions overlap each other, but Northlight can eliminate overlaps as usual. And so this query is answered by loading these regions from the dataset, which is better than loading the entire dataset, of course. Now, remember that these are two-dimensional examples. In practice, the datasets are four-dimensional, and you could also imagine that there's some pruning along the vertical axis, and there's also some pruning along the time axis. So in reality, this block decomposition has to happen in 4 dimensions, and also with a lot more blocks in practice. But that's not a problem, because we've built quite an advanced algorithm into Northlight to deal with these block decompositions, and you can see some plots right here. The first row is for 2D blocks, which is like the examples we've seen right before. And the bottom row shows 4D blocks, which is probably more common in practice. And on the very top row, you can see a few input examples. So the first one shows a row of aligned blocks. The second one is rather misaligned blocks. And the third column shows what we call the worst case for this algorithm. Now, if you look at the graphs, you will find some teal lines and some green lines. And the teal lines are the measurement results for a very naive block decomposition algorithm. And the green lines show the optimized algorithm that is built into Northlight. And you can see that even in the worst case scenario, Northlight can still handle a reasonable number of blocks before the optimization takes too long. And we'd say that for all realistic inputs, which are probably more of the first and the second kind, this will not be an issue, and query optimization will be done in under a second. Now, using the optimizations built into Northlight, you can do some tricks for query evaluation. And there's one trick I would like to show you right now, and that is what we call computing envelopes. This is a feature that's built into Northlight, and the idea is if you have a chunk of the data set, you can compute an upper and a lower bound along each dimension, and then you feed this bound into the query itself by means of a selection. Now, this selection doesn't do anything at all. It just wastes computation time at the moment, because it's always satisfied. We know the upper and lower bounds, and we know that every part of the dataset will always satisfy this predicate. However, if we now join this chunk of the dataset with a larger dataset, like the one from before, the SparkSQL optimizer will move this selection to the other side of the join. Now, I call this an induced selection. And furthermore, the SparkSQL optimizer will then push this selection predicate into the data source, which triggers Northlight's optimization and leads to only the relevant region of the dataset being loaded. And obviously, that's a huge saving in data loading. And you can see this in the runtime. So let's compare these two. The first bar shows the query time without the envelope computation we've just shown. So that takes up to 5 minutes for the entire query. This is just all due to data loading. And the second bar, like the green and the blue bar, shows the optimized pruned variant that uses envelopes. And you can see the time to compute the envelopes is negligible in comparison to the actual query time. And the actual query time is very, very low compared to the query time without envelopes. So using this envelope feature can make quite a difference in your queries. And again, this is integrated into Northlight, and computing an envelope doesn't even require having a dataset in netcdf format. So you can just use a CSV file if you want to. You can read the paper for more details if you like, or if you have any questions, just send me an email. Thanks for having me today. Have a nice day.